Is my lab 5. So the purpose of this lab was to observe a bar magnet that's going to fall through and induce a current in an aluminum foil tube. The time is going to vary in the magnetic field and provide an EMF that will create a current. And the following bar magnet will provide the source of the magnetic field and therefore the induced current, which goes around the tube. So the purpose of this lab was basically to model this interaction computationally and then compare those results to the experimental results that we calculated using Faraday's law. Some fundamental physical principles that I had to understand and use in order to complete this lab were Newton's second and third law, which is that net force is equal to mass times acceleration, and the Biot-Savart law that has to do with magnetic fields and calculating them, Lenz's law, which is basically used in Faraday's law, which is that a changing magnetic field can induce a current in surrounding objects. And in this specific situation, the aluminum foil is going to be what contains the current. The results that I got for this lab are that the average time for the magnet to fall through the tube are, experimentally I got 1.7 seconds, but computationally I got 3.99 seconds. This is the glow script that I wrote in order to calculate this using Faraday's law. So basically, I created an object for the bar magnet, and then I created a plot that's going to graph the velocity versus time, and then used a object for the tube and iterated over all of the different segments in order to calculate the flux for them. And I also used a lot of my concepts that I used in Lab 3 and calculated the flux at every point due to the falling magnet. So this is my final result from GlowScript. You can see on the left that's only the ending way that it looks, but it's going to move up and down throughout the graph as it's creating it, and then the right side is the final graph that was created. So my interpretation of this GlowScript code is basically that the intensity of the coloring on the tube is going to indicate the magnitude of the current flowing through each ring, and blue and red is going to indicate the current flowing opposite directions, and red is counterclockwise and blue is the clockwise current. And the dynamics of the system, if you flip the magnet around, basically the induced current is going to run in the opposite direction. However, the magnitude of the magnetic field would be the same. And then the magnet would fall faster in real life, and the system would actually be more accurate if you took into account the cardboard as well, because it's going to block some of the current. And then the computational system might be more accurate if I took into account the fact that while the magnet is still in the tube, the velocity is still constant, and so the forces on the magnet are constant and the acceleration is 0. And the magnet, when it exists inside the tube, the velocity is going to have a negative slope, meaning the magnitude of the velocity increases. These are my final questions that I answered, and thank you for listening to my lab.